Welcome to this biochemistry lecture on enzymes and their mechanisms of action. So as a review, the main function of enzymes is to reduce the activation energy of a reaction. And we'll get into a little bit more details on the kinetics in a later discussion, but that's the important part of what it's doing, of what an enzyme is doing. And you can see in this figure what you have is the ability of the molecule, in this situation an enzyme, to reduce the activation energy, which is right here, from a much higher state to a lower state. And so that translates into that is directly related to mechanisms of action. And the important part that we're going to see is we've discussed protein-protein interactions. These enzymes will engage in protein-protein interactions. They'll also engage in protein-ligand interactions or protein small molecule interactions. And what you're going to find is the size of the interaction is significantly smaller. So protein-protein interfaces are generally flat and large and rough, and they're about 1,000 to 2,000 square angstroms, whereas these enzyme pockets are very, very small, and they're between 300 and 500 square angstroms, and you can see that they have a lot of three-dimensional depth to them versus being very flat. And so molecules can fit nicely into those pockets. You can see that in this example right here, which I think is chymotrypsin, but it's not really the important part of the discussion. There is a binding pocket that exists that molecule is going to fit right into. It's called the active site. And there's a couple different mechanisms of action that exist, and that's what we're going to go over here. So there's, now, first and foremost, the simplest and most effective mechanism of action is just a proximity effect. And basically what an enzyme does is just brings two molecules together, and because they're close together, that facilitates the reaction, and the reaction goes from reactants to products more effectively. And that's a very simple way. It just brings them together. That's the proximity effect. The next mechanism of action we're going to discuss is transition state binding. And basically the theory behind this is that the transition state, in this situation you can see that we have a planar transition state in proline. That transition state fits better more geometrically and electrostatically in the active site than either L-proline or D-proline. And this fit provides a better energy state relative to the substrate and provides the ability for the enzyme to perform its work. So by binding the molecule in a transition state, it reduces the effective activation energy. In this situation, we're going from proline to pyrrole to carboxylate, and the transition state is stabilized, and that allows a reaction to occur more quickly. That's the theory with transition state binding. The next one is the lock and key mechanism. This is probably a little more famous than the other two, a little more defined. Basically, the idea is that the substrate only fits in there effectively at the active site. It's very specific, and it's called, the terminology is precise complementarity between the enzyme and the substrate. It acts like a lock and key. In this situation, you can see this in the enzyme. That molecule, that tetrahydrofolate, fits in the enzyme very specifically, and it binds in there. And it has the high degree of specificity is what allows the molecule to interact. So that's another mechanism by which you have that. It's a rigid three-dimensional body. The enzyme surface contains the active site. That molecule fits in that active site in a specific way in a lock and key with precise complementarity, and that's what facilitates the reaction occurring. The next one is induced fit, and this is hexokinase, and what you have in there is you can see that there's two different conformations of this protein. So there's the enzyme floating around, the glucose fits into the active site, and then the enzyme changes its shape, and then it causes an induced fit to occur. And so binding induces conformational changes of the protein. The active site is modified to basically accommodate the substrate, and that allows that reaction to proceed. It reduces the activation energy, and that second conformation allows the work of the enzyme to be done. We also can have binding of ionic intermediates. We're going to talk about this quite extensively as we talk about chymotrypsin or chemotrypsin, depending on your vernacular and regionalization. This is where we start talking about the catalytic triad as well, which we'll talk about in great detail. But the theory here is that we have a quasi-stable ionic species that can be bound by an ion pair and a hydrogen bond interaction. And so it's very similar to the transition state, but it's these ionic intermediates are what's bound, and those ionic intermediates have a lower activation energy than the non-ionic intermediates, and because they have lower activation energy and they're in proximity, and a lot of these things have specific additional mechanisms, including the proximity effect, and because there's neighboring acid bases and nucleophiles, and this is what you'll notice with the catalytic triad here, an acid-base nucleophile, those all facilitate, when they bind, those ionic intermediates bind, they facilitate that reaction. The catalytic triad is something you're going to want to know for your exams. It's very heavily tested upon, and basically you're going to have acids and a base and a nucleophile, and you can see all three of those with the histidine, asparagine, and serine. Right, so you have all three of those that are occurring. You can, the nucleophile is obviously the serine, and from there, and you can see the base is the histidine, and the asparagine is the acid. So you can see that those, and we'll go over a detailed mechanism of action here in a little bit, but that active site binds these ionic intermediaries, and there's an oxyanion hole in there with an intermediate binding or an intermediate catalyst, or not coenzyme or cofactor, and those allow those reactions to occur. They facilitate the reaction. This is a hydrolytic cleavage in this situation with chymotrypsin. So, and almost a large number of proteases do this. We talked about this. We talked about hydrolases. That's what used this mechanism. It's just a variation on this catalytic triad mechanism. So let's get into detail on this chymotrypsin. This was one of the first serine proteases, one of the first proteases characterized. We're going to go over each step. So the first step is substrate binding, which you probably will notice it looks very similar to a lock and key type mechanism or an induced fit type mechanism. And when the substrate binds, the side chains of the residue adjacent to the peptide, they kind of fit in this nice hydrophobic pocket, and that positions it for the attack. So you have a substrate that fits right in there nicely, and from there, that's the first important step. The next step becomes, so the next step in this, after the substrate binds, is we get a nucleophilic attack. And so basically the histidine 57 generates this nucleophilic attack where there's an alkoxide ion on serine 185. And so the ion attacks that peptide carbonyl group. It forms a tetrahedral acyl enzyme intermediate, and this short-lived negative charge on this carbonyl, which is stabilized by the hydrogen bonding in that hole. And that kind of stabilizes the reaction very quickly. From there, we get substrate cleavage based on that stabilization. So the instability of the negative charge on that substrate leads to the collapse of that tetrahedral intermediate, and we get a reformation of a double bond between the carbon and the amino group on the peptide linkage. So basically, effectively breaking that peptide bond. And it does leave some intermediates in there. The amino leaving group is protonated by the histidine 57, and that facilitates its displacement. But from there, we basically right now we're in an intermediate step. But we've basically cleaved the substrate off. So in step 4, we still have the acyl enzyme intermediate step. Water is going to come in, and in there, that water step is going to come in. It's going to be a very, very important part of the, it's going to transfer, it's going to form a nucleophilic attack on that hydroxide ion. That attack leads to the collapse of the tetrahedral intermediate and forms a second carboxylate anion and displaces the serine 195. So we have a short-lived intermediate deacylation step. We get an acyl enzyme intermediate. So right now we have an enzyme product intermediate that's in there, and from there, this is where everything starts to reset itself. So you get a breaking apart of the enzyme. That collapse, that tetrahedral intermediate, forms a second product, which is a carboxylate anion, again displacing that serine. And then the last step comes in, and from there, the whole product dissociates, and right there that regenerates the enzyme so that it's free to go. So the last step in step 6, we had an enzyme substrate complex that was formed, and from there we break off, and now we have the two separate, and the reaction is complete. That detail is important. Knowing that chymotrypsin detail is important, and that's the only enzyme mechanism we will ask you to do, but it's an important one. Hopefully you enjoyed this. We will look forward to seeing you in the next lecture.